So now I'm prepared to answer with math what happens to that rectangle as n goes to infinity. What happens to 2n minus 1 over n squared as n goes to infinity?
Yeah, it's really small, yeah.
Yeah, really small, like 0, right? Good. Okay, so fact. As n goes to infinity, delta x sub n goes to 0. So even the widest subinterval goes to 0. Alright, so if we're going to do this weird thing where we partition it into unequal widths, then we better make sure that they all go to 0. And we have done so by showing that the widest one goes to 0. Alright, so this is a kind of this is called a partition, a way of splitting up the interval from 0 to 1 up into subintervals. And I'm going to call this a good partition. There's no term for this as far as I know, so I invented my own one. Good. A good partition is one in which even the widest subinterval goes to 0 as n goes to infinity. So this seems good. Alright, having done all this background work, now we should probably just like do the problem. So if we're gonna, move it back to over near you, because I'm gonna flip forward a second. So how does this work out? We're gonna take the sum from I equals 1 to n, and then what is the area of the ith rectangle? What's the Berkowitz, what's the height of the ith rectangle?
It is f of 2i minus 1 over.
Careful, that's the width.
Yeah.
So yeah, what
Right, it's f of I squared over n squared.
yeah, we could be even more like simple about it, and we could just be like, all right, yeah, the height of the ith rectangle is the value of the function at the right-hand endpoint times what is the width of the ith rectangle? Just delta xi. Right. Yeah. So the area of the ith rectangle is the height of the ith rectangle times the width of the ith rectangle. And then, of course, we've developed formulas for these things. So f is the square root function, and c sub I was defined to be I squared over n squared. And then this we also have a formula for. It's like 2i minus 1 over n squared. All right, so now you see why we put in all this weird effort, because now that the square root is going to disappear, and then just finish off this problem. Go. Alright, so I think this like worked out, right? You get 2 over n cubed times this is n.
Wait, is it 2 plus 1 or 2 minus?
Plus 1 over 6. Yup.
No, I just,
Oh, wait, this is n, right?
You lost an I there.
I squared minus I.
You are all correct.
That's what I have now.
Yeah, so that's like right now. Cool. Okay, so math happens, and we get that's a 3, and we get a 2, and we get a zone 2, yeah. So this is 2n squared plus 3n plus 1 over 3n squared minus n plus 1 over 2n squared. Is that what you guys got?
Yeah.
Yeah. And if we take the limit, n goes to infinity of that answer. 2/3.
Like they all
They're not all 2/3. Whoa. Alright. Cool. So, on the one hand, we are awesome because we have solved this problem. So that's really cool. The other thing we realized is subintervals of unequal widths are like okay sometimes and might possibly be useful, or possibly never again. And now finally, let's call in some cool people. Raise your hand if you were cool and you thought of some cool, creative, weird way of doing this problem that avoided all this crap. Usually it's like 1 or 2 people per class. But I think this is what like you were talking about and you two and yeah, which one you already, you had your moment of glory. And which we do all talk all at once.
rotate x squared.
So it's like
make it polynomial.
This is even though this is a square root function, it's ultimately like a polynomial function if you kind of like square both sides or change variables or something. Yeah, the way I would think about it is to just put this in a box, which is like a strategy for finding the area of anything. Put it in a box. And now we see that the mysterious area that I was looking for is really what you get when you subtract out all this area, which is really, this is just like x equals y squared, right? You guys see what I'm doing here? Say yes. You do. Yeah, so what we could have done to solve this problem is just find the area between 0 and 1 of the x squared function. And that is something that we know how to do with our old methods. And now, if we attempt this, what would we end up with, by the way? We now know that this is in fact 1/3. And that's doable using our old methods, and then we could just subtract it from. Okay. Alright, cool. Good. Let's pause the video for a second, like hit the off button. And now a welcome.